Good morning. Let me know if there's any, if you have any questions for the start of class. Good morning, guys. Please make sure it's now 8 a.m. Please make sure you check into the um, attendance and let's begin lecture. So, seeing no questions for the good morning, um, we shall just launch right into what we are going to cover. And today, what we're going to cover is the periodic table. And on top of the periodic table, also just some general how to navigate formulas. We're going to go into that in a lot more detail, um, chapter 3, 4. But initially, this periodic table, which you guys will get to watch a video on how it was created. That video is already in Teams. I just need to link the assignment to it. But anyway, this periodic table was developed by Mendeleev. There are a whole bunch of other ways of aligning the material from the periodic table, but generally speaking, the periodic table as developed by Mendeleev in the okay, as developed by Mendeleev in the actually the early 1800s, is the table that has been the most frequently used and is the still the standard, surprisingly. Now, what Mendeleev did, he didn't know all of these elements assisted, the transfinite elements down here at the bottom. Most of those you had to have reactors to make, and so that those didn't start really being made until the 1940s, 1950s, and then into the 2000s. Um, even a lot of the even a lot of the transition elements, and certainly a lot of the lanthanides, actinides, those weren't discovered either until the the after Mendeleev's death. But what he did do was he recognized that when he when he started putting elements in order from their mass, but then also their reactivity. So he basically was ordering by mass, but creating columns that reflected reactivity. And when he had a gap where he had something that, say, platinum, which was known, or gold, so gold and iridium, which were found fairly uh, soon, he was like, okay, well, I have this thing that reacts like cobalt, and I have this stuff. Mercury was known really soon, and I have this stuff that reacts like silver, but I don't have anything that reacts like nickel in between these two, so I'm just going to leave it blank and assume that we just haven't discovered it yet. So that's basically what he did. He left blanks wherever there wasn't an element close to that mass that had the reactivity that matched the others in the column. And that motivated people to go out and start trying to hunt those, because it was like, oh, we're missing something. We haven't found an element, but we know it should react like iron or cobalt or nickel or copper. So let's go look for an element that let's go look at rocks and try to extract elements and see if we can't find one that reacts like this. So it was Mendeleev's periodic table was not just it was a historically important thing. It allowed the teaching of chemistry, but it also was a amazing guide to help find the rest of the elements. So it was a nice map to what was still missing. So I've borrowed this periodic table from a textbook from Silberberg, in fact, but basically it's got more labeling than we normally put on a periodic table, but you've got the main group elements, which are what we are the ones that stick up, basically. Um, then you have the transition metals, which are in the turquoise blue. You have the intertransition elements. Those, as chemists, we have very little to do with. And then you have some markings in terms of metalloids, nonmetals, metals main group, metals transition. Um, so, and hydrogen you will sometimes see also placed here on the periodic table because it can act like a halide in terms of reactivity, but it doesn't have a lot of electrons to give. We'll talk about that next time. But you can see it put over there. Now, what you need to understand as we move forward, and this is something you should begin by memorizing, but in the very next chapter, we're going to actually understand why this is. So these two columns are what are today more frequently called the S block. These 6 columns are very frequently known as the P block. The transition elements are more frequently known as the D block. And the lanthanides and actinides are more frequently known as the F block. And we'll get into why these names are applied in the very next lecture. But periods are what we call the rows. Groups are what we call the columns. Periods are defined by something called the principal quantum number. There we go. Which we will derive, well, we won't derive it, but we'll get into that. We'll get into where that arises in chapter 3. Groups are defined by reactivity. And properties. Okay, so group 1A or 1, and this particular periodic table has kind of the old nomenclature on the top, 1A, 2A, 3B, 4B, 5B. I'm not really sure where that comes from. The modern nomenclature is just 1, 2, 3, 4 number the columns across the periodic table, so much, much easier to deal with. So group 1A or group 1, so old nomenclature, new nomenclature. And because of that, let me flip this and call it group 1 and 1A. So new, group 1, old, 1A. These are called the alkali metals. And that's because originally they were discovered via base. And they have very basic properties, which is, again, a term you don't understand yet, but we will get to. And these generally form ionic compounds when they react. And in those ionic compounds, they tend to be +1 cations. So tend to form ionic compounds as a +1 cation. They are metals, though. So if you isolate them, they're soft, metallic. It is really hard to isolate them, and you have to be extremely careful handling them. And the reason you have to be so careful handling them is because they are so reactive. So they react with the water in the air. So generally speaking, if you have some, which I do in my lab, they're stored in oil to prevent any water from getting onto them. And you have to have a special fire extinguisher in your lab because they can burn in water and will burn in water. So they take a very special type of fire extinguisher to put out a fire if they catch on fire, which is not uncommon because when they react with water, they generate hydrogen gas, and they also generate a lot of heat. So you do generally have to be exceptionally careful handling them. They become less reactive as you move down the periodic table. So lithium is far more reactive than sodium, which is more reactive than potassium, and so forth. Okay, group 2, or 2A. These are less reactive than group 1A. These are called the alkali earth metals. And before you ask, yes, you need to know um, these names. They also tend to form ionic compounds. We'll understand this in Chapter 3, Chapter 4. But as plus 2 cations. So that takes care of the S block. I'm going to skip the transition metals right now. They are more complicated. Now we're going to move over to the P block. So group 13. Group 13 is a little bit weird. It doesn't have a special name that I know of. It's generally weird in terms of its reactivity. It can form covalent or ionic compounds, when we're going to talk about the difference there. So it can form covalent. I'm going to go ahead and emphasize this. So can form covalent molecules or ionic compounds. If it forms a covalent molecule, it tends to be, the bonds tend to be fairly polar and therefore fairly ionic in nature. That's all something we will cover. But you'll see you kind of go metalloids and then metals, and aluminum is right on that border between metalloid and metal. Metalloids are things that have some properties of metals and other properties not of metals. So they kind of form this little weird boundary between metals and nonmetals. If they are forming a compound, they tend to form +3 cations in ionic compounds or 3 bonds in covalent compounds. And 0 lone pairs. And you're not going to understand what lone pairs are right now. That's a chapter 3. I'm setting the stage for that in covalent molecules. So some of this is stuff we're going to cover a lot more in a lot more detail in the very next chapter and in chapter 4. But I'm setting the stage so you can go ahead and begin thinking about it. Okay, so I see that there's 16 of you. Most of you haven't said hi to me this morning. I will remind you to please check in. Your attendance is up, and it is linked in the check-in box. Okay. Group 14, or 4A, also doesn't really have a special name, which is kind of funny, considering how important Group 14 is. Yeah, it is a snowy morning for you guys. How important Group 14 is in terms of chemistry. Ironically, most of our true chemistry, our biological chemistry, is really started in period 2, row 4A, or group 14, i.e. carbon. But there is some speculation that on other planets you could have a silicon-based life, but on planet Earth, carbon-based is what formed. Silica is very much like carbon. Carbon is going to generally form covalent bonds. In a broad variety. And the reason for that is it's really hard to establish. It's kind of in the middle. So if it were to try to form an ionic compound, and you're going to see this as we swap over, it would either have to form a +4 or a -4. And it's really hard for very small atoms, which carbon is. The size of the atom gets larger as you move down the periodic table. It's very, very hard for a small atom with a small amount of protons. So carbon has 6 protons. It would be really hard for it to stabilize a +4 charge where it was only holding 3 electrons. Sorry, 2 electrons. Or a -4 charge where it's holding 10 electrons. Either one of those is just not really a great stable configuration for it. So because of that, it forms covalent bonds because it needs the electrons to stabilize itself quantum mechanically, but it can't just take the electrons away from something because it wouldn't be stable. So because of that, it has to share electrons with other things, and that's why it tends to form covalent bonds. I'm not saying that you won't ever see it in an ionic bond situation, but it's very, very rare. And I can't think of anything off the top of my head. It tends to form 4 bonds plus 0 lone pairs in covalent molecules. That kind of is the more standard configuration. Now, as you move from row 2 to row 3 to row 4, you can begin to form 4 bonds is the maximum amount of bonding you can have in row 2. So I'm going to go ahead and write that. Again, this is something we're going to cover in a lot more detail why, but row 2 can support 4 bonds only. It cannot do more than 4 bonds. It's quantum mechanically not possible. When you get to row 3, it is possible to do more than 4 bonds, and the farther down you go, the more likely you're going to end up with something with more than 4 bonds. 6 bonds tends to be the limit on how far up you go, just because of spatial limitations. There really is only so much area around a sphere where you can put something. So anyway, carbon, silica, that particular row, you tend to see it in 4 bonds. As you move down to silica, silica can support 4, 5, or 6 bonds. But again, a very stable configuration is going to be 4 bonds. You can occasionally see 3 bonds or 2 bonds, but that's going to be much less stable because you will have a charge on the element. So 4 bonds tends to be that nice, good intermediate for that. Group 15, or 5A, that's the one that has nitrogen in it. Now we're going to swap over to the nitrogen group can form covalent molecules, and it's more prevalent as a covalent in covalent molecules, but it can occasionally form ionic compounds as well. It's less prevalent as an ionic compound. So you can form covalent molecules or ionic compounds, but it's generally you're going to be less prevalent as an ionic compound. And that's because, again, in the ionic compound form, it's a -3 anion in ionic compounds. When it forms covalent bonds, it tends to form 3 bonds with 1 lone pair of electrons. That's kind of the standard stable configuration for elements in that particular column. Again, when you move down from nitrogen to phosphorus, phosphorus usually will form 3 or 5 bonds. And then arsenic, antimony, bismuth, they're 3 or 5 bonds. So 3 bonds with lone pair of electrons is nitrogen, and also a stable configuration for others. The period 3 or higher will lean towards 3 bonds or 5 bonds. Right. So, generally speaking, 3 to 5 bonds. But period 2, that second row, which is where nitrogen's at, 3 bonds, 1 lone pair. If it has anything other than that, it's going to be charged. Group 16, we finally are back to a group that has a name. These are the chalcogens. They tend to form -2 anions in ionic compounds, or 2 bonds with 2 lone pairs of electrons in covalent compounds. Now, again, if you're a group 3 or higher, period 3 or higher, it'll lean towards 2, 4, or 6 bonds. And again, we'll cover why that is. But generally speaking, when you get into the 3rd, 4th, 5th, 6th row in the chalcogen group, 2 bonds, 2 lone pairs is completely stable, but you might also see 4 bonds or 6 bonds in those particular groups, in that particular group. Group 17, or 7A, are the halogens. And like I said before, hydrogen can react like a halogen, so some periodic tables will put it both in group 1 and in group 17. So it'll put it in both places. And that's because hydrogen can be a +1 cation or a -1 anion, very stably. When it's a +1 cation, it acts like an alkali metal. When it's a -1 anion, it tends to react like a halogen, so they tend to put it in both places. Halogens. Halogens are -1 anions always in ionic compounds. And they tend to be one bond with 3 lone pairs of electrons in covalent compounds. Now, period 3 or higher, again, this leans towards a huge different amount of bonding. I was thinking in terms of structures, so give me just a minute. One bond, I think it goes, this one's the most diverse, and we'll come back to it. So, and you'll even see that when we talk a little bit about nomenclature, because while we're going through things that you kind of need to memorize, I'm going to go ahead and add the other thing you need to begin to memorize. Now, I think I mentioned last time in terms of what you need to memorize on the periodic table at this point as freshman chemistry. Now we can talk about this in terms of the group names. You need to know, in essence, for memorizing, names and symbols of first 3 rows. So these first 3 rows of the periodic table, you should know every name and every symbol. Then the nonmetals. And now, in terms of the rest of the periodic table, it's going to be kind of pick and choose. And the truth is even for the nonmetals, we kind of end our memorize right here. And the reason for that is you'll notice the other ones have their masses in parentheses, and that's because they're radioactive, and as such, we tend not to work with them in the lab or handle them that frequently. So these row 6, row 7, there's very few things in row 6 or 7 that you're going to be asked to ever handle, work with, deal with, or get to look at. And most of those will be in the transition metals. And for most of those, we're going to be leaning towards you will memorize them next semester, not this semester. But using this blue line as your cutoff line, the symbols of the names and symbols of the first 3 rows and all the nonmetals above the cutoff. And also above the cutoff, group 1A, group 2A, and then there will just be a handful in the transition metals. But definitely group 1A, 2A above the cutoff, and all the nonmetals above this cutoff blue line, which is basically inset xenon. Um, that will get you almost all of chemistry with the handful of transition metals we'll talk about in just shortly. So, okay. Now, group 18, 8A, these are called the noble gases. They are, for the most part, non-reactive, which means they don't form bonds. The exception to that rule, so no molecules or um, ionic compounds, generally. There is an exception to that. Xenon will form molecules with fluorine and chlorine. These are highly reactive molecules, but they are used. Xenon tetrafluoride is a solid. They are used to actually halogenate organic compounds, so you will run across them in the lab, in some labs. So they do exist. The reason why is xenon is huge. So it has a lot of electrons, so it just doesn't really have a problem sharing a couple of those electrons with other things to form a molecule, a covalent bonded molecule, especially with things that really, 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 really want an electron. Um, so it will form molecules. The other ones will not. So that's the S block and P block. And most of chemistry, most of the pharmaceuticals that we make, most of the chemistry that goes on in our body pretty much involves just the S block and P block. There are a handful of transition metals that are important in chemistry. And the reason why I left the transition metals for last is because they don't have they they don't have a pattern like that. They're not as straightforward as what the S and P block elements are. in terms of bonding and things like that. Okay, we're going to take a 5-minute break where you guys can ask some questions, and then we'll go on to the next step, which will be the transition metals. Let me look at the questions you guys asked last week and flip us over to uh, so I'm posting the announcement for week 4 questions. Okay, I've put in the breaker for week 4. I've reminded you to not reply in the announcement for week 4 questions, but just post your questions. I will remind you again that office hours and BD and the body doubling will be tomorrow evening, and homework will get posted this afternoon. So I suspect you guys might have questions. After all, you're snowed in, so. Uh, the homework's going to be worth a little bit more than 10 points per homework set, and it's probably going to be due every other week, is the way I'm leaning in terms of the schedule. So that gives us a little bit, few more lectures to cover. How much snow did you guys get so far? Because I know it's still snowing. I know it's still blizzard warnings. Wow, Dwight, that's huge. Oh my God. They said They said it depended on where you're going to be out. I expect where my house is out, which is out on the east side of Long Island, so closer to the Atlantic Ocean. I suspect they got 2 feet or more. Because New York City was supposed to get less than out in Suffolk County. Yeah, it strengthened overnight and it didn't shift as far out to the ocean, so I suspect it's still going to be falling for a little bit. And the dry air they thought might filter in didn't. Like over the next few days. Oh, hopefully not. So I will be grading the first homework this afternoon and into evening and into tomorrow. because I have to go sit in offices tomorrow. So expect your grades to be up by tomorrow evening for the first homework. Okie dokie. Seeing no questions, let's get back to this. There are very few instances where you can memorize and be okay in freshman chemistry. The way the Adams First approach works in terms of chemistry is the memorization is front loaded in the course. That means that over the next few weeks is where you'll spend more time memorizing than you will for the rest of Gen Chem 1 and 2. But the advantage to that is it means that the first exam tends to be more similar to a biology exam or earth science exam, where it's more conceptual, less mathematical than the second or third exam are. So what I'm saying is you guys need to break out the flashcards for this material. So it's really important you memorize it. This stuff has to be memorized because it is the foundation that you build the rest of chemistry on top of. So if you do not memorize this, you are not just hampering your ability in this class, you are hampering your ability to pass Gen Chem 2, Orgo 1, Orgo 2, and any other chemistry class you take. So the stuff we're going over in the next few lectures, absolutely flashcard it, absolutely memorize it. It is kind of it's like addition and subtraction of numbers. It's one of those things that everything else relies on. Okay? So, with that being said, now that we've covered the S&P block, let's look at the transition metals. Now, the reason why transition metals generally are not involved that much in chemistry, and the truth is ionic compounds, you're more likely to see certain ionic compounds in biology because they provide important minerals to the body in nutrition than you are in chemistry. And the reason is the bonding is just not that complex, and you can't make that many interesting new things, or so we thought. But lately, with more modern synthetic techniques, the things you can make by making alloys of metals or ceramics, which are ionic compounds, turn out to be a lot more interesting than chemists really thought. But they tend to be interesting in terms of materials. And because of that, I don't understand your question. But because of that, the transition metals tend to fall by the wayside in chemistry. And if you really got interested in them, you would study them in a course called material science or a program called material science, which tends to be in engineering. You would spend a lot more time studying solid state material, and you would also spend time doing uh, and you would also spend time learning about the structure of solid states. So that, speaking of which, the transition metals as chemists we usually only actually work with kind of the first row of the transition metals. Alloys, since this question was just asked, although I don't think from a student in my class, alloys are mixtures of transition metals or of metals in general that form a true solution, solid state solution. And we will cover what a solid state solution is, but I think we cover that in general chemistry too. But so alloys are solutions of different metals. Okay, so the transition metals as a whole, the ones that we will deal with, the other issue with transition metals when we get to nomenclature is they tend to exist as, they're almost always cations. So they're always positively charged when they form. So they're almost always going to form ionic compounds when they form a compound. And the issue is they just tend to have different charges when they form ionic compounds. So you have to know, this is one of those instances where you just have to memorize which metals form which charges. There will be, when we work with it in terms of electron configuration in the next chapters, you will begin to be able to see why certain metals form certain charges. But in the end, having to rethink your way through all of the electron configuration is just a pain. It's easier just to memorize this. So which ones do you need to know and memorize for first semester? So titanium, usually this is not a common metal that we use in chemistry for reactivity. It's a very common metal used in materials because it has very low density, so it's very light, but surprisingly strong for how light it is as a metal. Now, it tends to lean towards +3 and +4, which is a little weird in terms of ions. Titanium 3, I think, is more common than titanium 4, but I'd have to check that. Vanadium, I've never even held a compound of vanadium in 20 years of teaching or working in labs, so that one we don't usually have you guys memorize because why? Chromium, though. Chromium is actually, again, it's one of those that's way more common in alloys and than in ionic compounds. But you guys are going to be familiar with chromium because chromium is where the word chrome comes from. So the really, really shiny pieces on cars or semi-trucks, but cars, so that really shiny metal, what they do is they take aluminum and they put it in an electrochemical bath and they plate chromium on top of it. And they do that because chromium as a metal is really, really shiny. The other place where chromium is really important is in stainless steel. It's in fact why stainless steel has that stainless property. It's the reason why stainless steel doesn't rust. And that's in fact why they put chromium on car parts, is because chromium doesn't tend to form oxides, which means it doesn't tend to rust. And that's why it stays shiny on as a thin coating on bumpers and things. So chromium doesn't tend to react with oxygen and form oxides. So it's an important additive in steel. It's an important coating because of that. In ionic compounds, it is +2 +3. The next one you definitely use and you will handle in freshman chemistry, and that is manganese. Do not confuse manganese, which is a transition metal, with magnesium, which is a alkali earth metal. Very important. Magnesium is Mg, manganese is Mn. Very, very important. Don't mix those two up. Very different chemical reactivities. Manganese tends to be +3 +4 or +2 +4 in terms of its cations that it forms. Iron, this one students get wrong very frequently. You need to memorize this. The symbol for iron is Fe. It's a 2 plus or a 3 plus as the most stable cations. It's symbolized by Fe for ferrous, which was what the Latin word that was used for things that were magnetic. We still use ferrous for magnetic. In fact, we call anything that's magnetic a ferric metal. But iron is certainly magnetic. So it's it was the first example of that. That's why it was given the name ferrous in Latin. We call it iron. It's the dominant um, metal in alloys of steel and stainless steel. So it's the main metal. It's also the dominant, if you guys ever go to a place that has red clay or red mud, so in the South, that soil has a huge amount of iron in it. That red is characteristic of iron 3. Iron 3 oxide is red. So if you have a lot of iron 3 oxide, it's going to be red. That gives you red clay in red clay pots. That gives you red for painting. It's very common as a pigment. So that is iron. Next one is copper on that same row. Copper was named cuprous in Latin, so Cu, and it's a +1 or a +2. It was named cuprous because green, its color. Statue of Liberty, that's that copper, that green that you see on the Statue of Liberty is copper oxide, copper 2 oxide. So it's a very specific shade of green. Nickel, it is +2 +3. You'll notice almost all of these ions have a stable +2 except for titanium. And the reason for that is because it's very easy to pull those 2 electrons off because of that S block that's before the transition metals. We are going to cover that. But that's why the +2 is apparent in all of these and isn't very stable. And there is a titanium +2. It's just more rare than titanium 3 and 4. Oops. It actually goes nickel copper. There's a one in between. It's one that's not very common. Um, And it is one that we don't generally require you guys to know, but I do want to put these in the correct order. So cobalt is the one between iron, nickel, and copper. Cobalt's +2 +3. Um, the truth is on cobalt, I wouldn't expect you to memorize. At this stage. It's very uncommon in a lab. Zinc, on the other hand, is very common. Zinc is +2, only +2. It's very common in the lab because you'll see zinc as a metal placed on other metals to prevent oxidation, to prevent rusting, especially in saltwater environments. And that's because it it forms a really good oxide, so it's going to be more reactive and attract and form the oxides versus the other metals. So it's a really good way of protecting the other metals, i.e., it's going to react first. So, and it also in that reaction is going to provide electrons to the other metals to prevent them from reacting. So it's a very nice compound in that regard. In terms of the rest of the periodic table, the ones that you need to be familiar with are silver, which is arginine in terms of Latin. I'd have to look it up. It only forms a +1. So these are lower on the periodic table. Gold, Aureus for the sun. It forms a +1 and a +3 in both common. Let's see, any others? In terms of ions, only mercury. But so in terms of ions, the only other one that is important for this class is mercury. We don't work with mercury that much anymore. It's very weird because the 2+ cation is stable as an elemental cation. The 1+ is forms a molecule. So the +1 charge mercury cation actually isn't a single atom. It's a molecule. It forms a dimer, a mercury dimer that then is a cation. So it's very strange. Now, the reason why it's so important to begin to memorize these is because of how we name these. So, for instance, when we get to nomenclature, not that long from now, if we were to see something like this, and this will allow me to go into the next stage. If we were to see something like this versus this, we have to be able to distinguish these two. Sorry. There we go. These are two different ionic compounds. The first one we would name today, mercury 1, because it's the +1 charge on mercury oxide. This one we would name mercury 2 oxide. And in the old names, this would be mercurous oxide and mercuric oxide. The reason why they went away from the us and the ick was because for mercury, us is +1 and ick is +2, but for iron, us is +2 and ick is +3, and for titanium, titanus would be +3 and titanic would be +4. And at some point you're like, this is just, as a nomenclature, this is so confusing. And it actually requires way too much memorization to accurately name something. And so what they did is they just decided we're not going to do it this way anymore. We're just going to put the charge of the cation as part of the name. So when you see mercury 1, you know that's the +1 charge of mercury. And so you know it is this dimer, this molecular dimer. If you see mercury 2, you know that's the +2 charge of mercury. That's this. So that means as you begin to memorize these, you might want to go ahead and begin to memorize if you need to. Some people don't, others do. You might want to go ahead and begin to associate the cations with their names. And I won't ever use the old nomenclature on exams. That doesn't mean that you won't see the old nomenclatures on really old bottles of chemicals. And occasionally some companies will still name stuff based on the old nomenclature, but they will also use the modern IUPAC required name as well. So you're safe either way. Now, while we're here, let's use the periodic table to calculate. Let's talk about what a mole is, and then also use the periodic table to calculate molar mass. So last time we talked about kind of average mass and isotopes, and I used something called an atomic mass unit. Which in physics we abbreviate as AMU, and which in some chemistry books they just abbreviate as U. Now, an atomic mass unit, so 1U or 1 AMU, is kind of the mass of a proton. So it's 1.66054 times 10 to the minus 27 kilograms. And that's really small. I mean, that you're not ever going to weigh that. You're not ever going to come close to weighing that. So when we talk about the mass of gold 197, and again, let's go ahead and review. So if it's gold and it has a mass of 197, because it's gold, if I go up to my periodic table and I look, gold has an atomic number of 79. Gold has an atomic number of 79, which I could put down here. And that means for metallic gold, which is neutral, the number of protons is 79. The number of neutrons is 197 minus 79, or 118. And the number of electrons, since this is neutral, is 79. But what's the mass? If I have one atom of gold, how much does it weigh? Of this particular isotope of gold? Well, it's 197 AMU. Now, what I'm about to show you, this is the way I work this. And I work it this way because it allows me to check units. It's really, really important that you get in the habit of writing units. It's really, really important that you get in the habit of checking units. Because if your units, you know what units you're starting with, the problem's generally going to tell you what units, what the answer it wants. And that, like for this instance, I want mass of a single atom of gold. So I know that mass is going to be in grams or kilograms, but grams is generally the unit of mass we use in chemistry, not physics. So that means I know I'm going to a unit of grams. So if I write my units and do this in this particular way, if my units don't cancel, I know I've made a mistake. Now, I know I have this relationship for AMU and to grams. And if I want AMU to cancel, just like any fraction, I want the AMU on the bottom. And that means on the top is the other value. Why? Why can I put that number on the top? I will remind you mathematically that if I have A equals B, if I divide both sides by A, I get 1 equals B over A. And I will also remind you that anything multiplied by 1 is the same thing. So if I take 197 AMU and multiply it by 1, I still have 197 AMU. And in essence, 166,054 times 10 to the minus 27 kilograms divided by 1 AMU is 1, based on this formula up here. You're like, what in the world is she talking about? What's causing the change in the number is the change in the units. The number will be different because the units are different. Now, because this is chemistry and I want my stuff in grams, not kilograms, I have to remember in 1 kilogram, K means 1,000, that's 1,000 grams. And it's the same thing. This second, what's called conversion factor, so this is called a conversion factor. This is also a conversion factor. And it's coming from the relationship that 1 kilogram is 1,000, that's the K, grams. How do I know which order to put this conversion factor? Because I could have also up here divided by B. In other words, I can write this as 1,000 grams over 1 kilogram. I could have also written this as 1 kilogram divided by 1,000 grams. No equal sign there. Those two are not well, technically they are equal. They're both 1, but the units don't. Well, yeah, the units cancel too. But anyway, how do I know which one of these to use? I need to convert kilograms to grams. That means grams needs to be on top. I have kilograms on top. I need the kilograms to cancel. So that means the kilograms need to be on the bottom. This is how you do this. So that gives me 3.2 times 10 to the minus 22 grams. That's a really tiny number. And you can imagine, first of all, you are not going to be able to weigh that. You're not going to be able to transfer that. You're not going to be even able to see that by eye, that amount of gold. That's 1 atom of gold. So what can I do in order to make this easier to deal with? That's what chemists were approaching with. These are really, really small numbers, so how can I go about getting these numbers up to something I can measure? Where I'm not having, and think about it even from a more modern perspective than when this was first developed, uh, of, well, they had, anyway, think about this when you're typing this, even today. I mean, think about how you have to actually hand type this. If I were to go to this and type it, I have 3.27. Now I need the times. And X doesn't work. I need the actual time symbol. So now I'm going to have to go hunt a symbol for times and insert it because I need the times symbol. And then I need the 10. And then somehow I've got to get the minus 22 as a superscript, grams. So now I need to go back and either superscript this. This is a pain. So, and technically I need the minus sign, not the little dash. And this was a pain when people were trying to typeset this long ago with manual typewriters and then electronic typewriters, and even in modern computers, this is not so easy to typeset. So what can we do to scale this, to get it bigger? Well, the decision was made, and the original decision was made, we're going to tie it to oxygen. Today we tie this to carbon. So our definition of what a mole is, originally we tied to something, to carbon, to oxygen. And then in the 70s, we decided it would be much easier to maintain the standard of what a mole is if instead of tying it to a gas, we tied it to a solid. And carbon is a very stable solid. And the dominant isotope is 99% of the isotope that you get when you measure carbon is one isotope. So carbon is a much more stable standard to tie a unit to. So what we defined was, we said we are going to define a number where carbon 12 is exactly 12 grams. Um, so where we're going to force the mass of the carbon 12. So basically what we did is we said we are going to force the mass such that 1 mole of carbon 12 is exactly 12 grams. And this is how we define a mole. Now, carbon 12 has for AMU 12.000 AMU. We just worked out that AMU is 1.66054 times 10 to the minus 27 kilograms in 1 AMU. We've got 1,000 grams and 1 kilogram. So that means in so for 1 mole, we get 12 AMU of carbon is 1.66 times 10 to the 24. Now, that's in 12, so that's a 1 atom. So that means 1 atom of carbon 12 is 1.66054 times 10 to the minus 24 moles. Now, let's flip that. And ask how many atoms of carbon 12 are in 1 mole. So I've got this many moles of carbon 12 in 1 atom. how many atoms of carbon-12 are in 1 mole. So I need to get 1 on this side. So I take 1 atom, 12 carbon, divide it by 1.66054 times 10 to the minus 24 moles. And I get 6.022 times 10 to the 23 atoms of carbon-12 per mole. And we are just going to define this as a new constant called Avogadro's number. And we are going to scale the masses of every compound relative to this number. Could we have chosen something else? We did. We, for a long time, did exactly the same thing, but using oxygen. We just said that 16 AM, the mass of one oxygen 16 atom was going to be our conversion factor instead of the mass of one carbon-12 factor for the mole. And it made a subtle shift in the masses, not huge, but a little. Because everything on the periodic table is measured relative to this. So that means that now we have a standard definition where we define Avogadro's number as just in general 6.022 times 10 to the 23, anything, particles, you name it, molecules, atoms, so anything per mole. So basically that's, anytime you have that large a number, that's how you define a mole. And students struggle with the mole. And they struggle with it because you look at that and you go, well, what is it? It's a made up number. It's a scaling number. We don't want to typeset 10 to the minus 27 all of the time, and we know we can't measure that, and we know we're not measuring a single atom, we're measuring a whole bunch of atoms, because we're measuring 1 gram, we're not measuring 10 to the minus 22 grams. So we're going to scale the amount of atoms up to a measurable amount and understand that we're always going to be looking at, when we measure something in the lab, we're never going to be looking at a single atom, a single molecule, a single anything. We're going to be looking at a bunch. How much is a bunch? Oh, 10 to the 23, roughly. In the gas, 10 to the 18. 10 to the 18. Liquid water's 10 to the 31. Well, that's particles per milliliter. That's density. So, it's a lot. There's a lot of particles in a milliliter of water. So it's a scaling number, in other words. And it's defined in such a way that we could easily just use the values that we'd already calculated on the periodic table where we were using atomic mass units, but now those values are more measurable. So that means now when I look at the periodic table for carbon, and we already know that this is an average mass, and we worked that out last time, 12.011 AMU is also 1 AMU is now 1 gram per mole, this newly defined mole, and that means I now have 12.011 grams per mole. And grams per mole, much easier to work with, except I had to do what? I had to make up a scaling unit called moles, which basically does what? It takes all of that times 10 to the minus 22 and builds it into the actual unit. That's what it does. So much like I told you, we write kilo where we don't have to typeset 10 to the 3. We write milli where we don't have to write 10 to the minus 3. We developed moles where we don't have to write 10 to the minus 27 all of the time, in truth. So this gives us an easy way to convert between grams and a quantity-based approach. And that was important because if I look at 1 gram of carbon versus 1 gram of nitrogen, do they have the same number of particles? So if I look at 1 gram of carbon, now I can do this fairly easily, 12.011 grams in 1 mole. And using Avogadro's number, I know I have 6.022 times 10 to the 23 carbons in 1 mole. Versus if I do nitrogen, one mole, 14 point, I think it's 007 grams, and 6.022 times 10 to the 23 nitrogens in 1 mole. And that means I have 1 div 12.011 times 6.022 e to the 23. Calculator decided to stick. So if you're really wondering, we can actually make up units on our own? Yes, you can. And if those units turn out to be incredibly useful and other people begin to use them, then it gets your name. But when you are making up and using a unit that nobody else uses, you have to define it in every paper that you use it in. And then over time, if other people decide it is a useful unit and begin to use it, then that unit becomes more standard, and then it becomes something that gets taught, and then it becomes a new unit. So you can see 1 gram of carbon contains more carbon atoms than 1 gram of nitrogen. So but when you're working with it in a lab, you just have 1 gram, and that's what you know. So we understood that we needed a way of scaling mass to amount. You see, because if I'm looking at 5 times 10 to the 23 carbon and 4 times 10 to the 23 nitrogen, I'm saying, well, I don't have, if I'm looking at mass, I'm like, okay, I have the same amount of carbon and nitrogen. The truth is you don't. You have more carbon than nitrogen. So we needed a way of being able to scale the amounts, the number of atoms, the amount, which is fixed, to the mass that we measure in the lab. And we wanted it so that it was a standard transition and everybody would accept it and use it. And that's basically what a mole is. So yes, it's technically a scaling factor that scales up all of the per atom masses to a larger value that is lab measurable. Um, that's what it does. And that's why students really struggle with it, is because it's a made up number. I mean, there's no way to get around that. It's a number that is created and used because it's convenient. And it makes working with chemicals in a chemistry lab, doing synthesis, easier. And that's why we use it. Now, ironically, at this stage, until I see you guys again, if you decide to become chemistry majors and take PChem, and we derive a whole bunch of the formulas we're going to use from first principles, we, as chemists, do not ever work in a per atom base. We are always working in a per mole base, in a molar base. And that means the truth is do you really need to memorize Avogadro's number? No. Why? We don't actually use it that frequently. Why? The periodic table's masses are already in a gram per mole base, and we just use grams per mole. And we write all of our chemical reactions in per moles. Um, those same reactions you could write as a per atom, but why? Then we can't measure that in the lab. So all of our reactions, when we start balancing them, they're going to be per mole. And that means we can use fractional balancing numbers because we're not balancing per atom. So it just made chemistry easier to do. And at this stage, you just, from a chemistry perspective, you don't really use Avogadro's number that much. About the only place you use it is sometimes for talking about gas phase density. But other than that, um, you need to know it's there. You need to know how to scale and get between mass to moles to atoms. I'm showing you how to do that there. But it's very, very, very rare that we ever talk about something as atoms per basis. It's almost always a molar basis. Now, I did just say that density is one of those things that you will see in units other than, so that is one that I will go ahead and come back to. Density is something we covered in chapter 1. So the density, I'm going to use rho. We normally in chemistry use it as a mass density. And generally speaking, you are not going to see a sub M on that. You're just going to see a rho or a D. And it is mass of A per volume of A. So it has units of grams per milliliter is the standard units for density. And I'm making a big deal of A here because eventually when we do concentration and solubility, that will be mass of A per volume of B. So that's a different unit. But there are other densities. There's mole density. Mole density, that would be a sub lowercase n. This would be moles of A per volume of A. And it would have units of moles per milliliter. This tends to be standard for liquids. This It would actually be convenient in liquids, but it's predominantly used in gases. But it would be really convenient if on bottles they would put it for liquids, just because we generally need moles, not mass, but they don't usually. So this is mole density. Density just means per volume. And then you also have number density. And number density, we usually don't put a sub in, but I'll put a capital in there. This is number of particles of A per volume of A. And this is particles. And here you usually use cubic centimeters instead of milliliters because if you're going to go all the way to particles, you might as well. Milliliters and cubic centimeters are the exact same unit. I'm going to remind you of that. 1 milliliter is 1 cubic centimeter. But when people are using particles, they tend to use cubic centimeters. And this tends to be gases, and it tends to be a popular unit in physics. And it's called number density. Now, all of these are interchangeable. Let's look at how to do that in our last 10 minutes. Let's look at this for water, because this gives us a good opportunity to see how to work with this. So the density, the mass density of water at room temperature is 1.00 grams per milliliter. The molecular formula for water is H2O. Now, first thing I have to do in order to convert grams to moles is I need a conversion factor. Because that's a unit conversion. Now, we've had a conversion factor that lets us do that. This periodic table mass, AMU, but this isn't for an element on the periodic table. So the conversion factor here is called molar mass, and the way you get, or molecular weight. They can be done interchangeably. And the way you get that is, first thing you do is you look on the periodic table and you get the masses of the elements. And for oxygen, it's 15.998 or 999. Um, Now, just so you know, you're going to have certain of these molar masses memorized by the end of Gen Chem. You don't have to memorize them. You just use them so much. So these I happen to have memorized. Now, that's from the periodic table, but I have 2 hydrogens for every 1 oxygen. And that means I need to multiply the top one by 2, the bottom one by 1. So you multiply by the number of elements in your molecular formula. This is called a molecular formula. So that gives me 1.18 18 0.014 grams per mole. And if this is a 9, it would be 0.16. And this is the molar mass of water, or the molecular weight of water. And we tend to symbolize this by a very fancy cursive M. And because each compound has a different molar mass, you'll usually see this written when you're when you're working on it. You can write this as the molar mass of water is 18.014 grams per mole. Now, as we progress through this semester, you are going to be calculating molar masses all of the time. And in fact, what I usually tell students when we get to the chapters on stoichiometry is the very first thing you should do is just go ahead and calculate the molar mass for everything, because you're probably going to need it. And it doesn't hurt and it doesn't take that much time. And if you go ahead and do that at the very beginning of the problem, you have what you need and you don't have to change directions in the middle of the problem to do that calculation. So it's just one of those things that kind of saves time in swapping directions. Now, do you have to show it in the detail I've shown it above to get credit? No. I'm going to presume by the end of very soon, you're going to be able to do that without showing all of your work. I mean, you have got the numbers on the periodic table, you have a calculator. So I'm not going to be grading the work, I'm going to be grading the answer that you get from that. Just going ahead and answering that. So that means now I have a density of 1.00 grams of water per milliliter of water. That's what density stands for. Now, if I take this and I take 18.014 grams in 1 mole, this is 1 mole of water has 18.04 grams of water. Grams cancels. It gives me moles per milliliter. So 1 divided by 18.014. So this is 0.0. Now, start it with 3 significant figures. This is a multiplication problem, so should end with 3 significant figures. 5, 5, 5 moles of water per milliliter of water. This is molar density. Now, if I take my molar density, 0.0555 moles of water per milliliter of water, and I have 6.022 times 10 to the 23 waters in 1 mole of water, and I have in 1 milliliter of water 1 cubic centimeter of water. Now, do you have to write this second unit conversion? Not really. You know that a milliliter is a cubic centimeter. You can kind of use those interchangeably. So this is 3.34 times 10 to the 22 water molecules per cubic centimeter. which you will generally see written, so this is number density, as 3.34 times 10 to the 22 inverse cubic centimeters. Notice I just dropped the water molecules. So this is the number density. Now notice the significant difference in scale. I went from 18, I went from 1 to 0.06 to 3.3 times 10 to the 22. So that means that gives you a good idea of why we sometimes don't write the subscripts on density. Because if you're looking at a density and it's, 1, 2, 4, 10, it's probably in grams per milliliter. If you're looking at a density that's 0.06, 0.07, 0.04, 0.03, probably molar density. And if you're looking at a density that's times 10 to the 20 something, that is definitely number density. There is nothing that has a density of 10 to the 22 grams per milliliter except the plasma of the sun, or maybe the Jupiter. So you don't have to worry. If you see 10 to the 20, you know that that's a number density. Can't be anything less other than that if you are on Earth and you are talking about Earth. So generally speaking, when you read about densities, all of these are just going to be given the same symbol of rho. They're not going to be, it's not going to be rho sub m or rho sub n or rho sub capital N. It's just going to be rho. And they're going to expect you to know in context if it's, and based on units, because a scientist isn't going to drop the units, they're going to tell you the units. But generally speaking, once you get used to this, you're not going to need to see the units to know which type of density it is, because you're going to be able to tell by the size of the number that's in front of the units. So that is molar mass, and that's how you calculate molar mass. Now, based on my textbook, the only other thing that is in Chapter 2, besides molar mass and formula units, is mass spectrometry, which we do not cover. I am going to give you an optional homework on that. That would be a bonus homework, but it is not something that we are going to cover or that's going to be required that you know for an exam. So it's going to be something you can read for bonus. But that is how, mass spectrometry is how we know what the masses of isotopes are. It really is. It's also how we find the masses of new molecules that we make. And it is one of the requirements when you make a new molecule and you are going to publish that new molecule in a journal. One of the things you have to do is you have to get the mass of that determined via mass spectrometry to 4 decimal places, which is high resolution mass spectrometry, and it's very expensive. So like my colleagues that are organic chemists, they'll send out like 100 molecules to somebody that has a high resolution mass spec, and they have to pay, $100 per molecule for that. So it's not inexpensive, especially if you've got like 50, 60 molecules that you need this measured. Sometimes you can negotiate a better rate than $100 per molecule, but it's still not inexpensive. But on the other hand, it's not inexpensive to maintain a high resolution mass spec instrument, because it can't have, if you're going to measure mass of things to 4 decimal places, then that instrument has to be exceptionally clean and be maintained as exceptionally clean. So it's not an easy instrument to maintain either, which is part of the reason why it costs. Okay, so we are pretty much done with the Chapter 2 out of Gilbert. We will be moving to Chapter 3. Next lecture, chapter 3, is our beginning of quantum mechanics. So we'll talk about electromagnetism. We will talk about electrons and how they were discovered and the history of how the atom was discovered. And then talk about why the periodic table has the structure it has. Why do the alkali metals really want to be +1 if they're going to form an ionic compound? Why do the alkaline earths, why are they +2? Why does that periodic table, why does the reactivity really divide the way it does? Why is the periodic table shaped the way it is? Turns out that Mendeleev got it right. He was doing that all empirically, but 100 years after him, when we finally understood quantum mechanics, it turned out that he got it right, that the shape of the periodic table and the way it's structured really is a brilliant guide for the quantum mechanics of the elements. And since the quantum mechanics is what determines the bonding, it's a really good guide for the bonding. Um, so I always am amazed by that. Anyway, that's the end of the lecture for today. Um, I will see you guys on Wednesday, but not personally. We will be talking about this in terms of we will be meeting online again. And I'll see you tomorrow if you choose to come to office hours. So have a good rest of the day. Don't get buried in snow.